Use the streams again, the encoder, to learn different ways of processing for each type of object. For example, trees will be treated differently from cars. The resulting feature tensors are further processed by residual blocks, which output tensors at multiple scales. Let us now look at the image enhancement network.
Who the hell understands this? I'm gonna play. I ain't gonna do y'all right there.
To see what we can do with these multi-scale tensors. The enhancement network is based on HRNet, which processes images at multiple scales in parallel. Each scale of the feature tensors matches a scale in the network. The network consists of many residual blocks at each scale. Within the residual blocks, we replace the batch normalization layers with our own rendering-aware denormalization blocks, or RAD for short. The RAD layers modulate features based on the rendering information.
I'm sorry, I can't do it, yo. I can't do it. I'm not about to sit here and have people listen to this. I'm not about to do it, okay? I'm sorry. We're not about to do it. It's over with. I'm not doing it. I can't do it. I tried. Who wants me? Hold on. Let me take a poll. I don't want to be that guy, okay? But I feel like that guy right now. I don't understand what the hell is going on. Maybe I need to So, hold up. Who wants to continue watching this video? Let me know right now. If you want to continue, put continue. If you say stop it, I'm stopping. Okay, Kyle. That's it. It's Kyle, all you had to say. Young OG said play the video. That's it. I'm going to go ahead. I'm not even going to do the business. And you're right. I started playing the video. The least I can do is finish it. You know what I mean? Kyle's right. It's too late, y'all. It's too late, Dead Specimen. You ain't got none. Kyle said so.
Blocks at each scale. Within the residual blocks, we replace the batch normalization layers with our own rendering-aware denormalization blocks, or RAD for short. The RAD layers modulate features based on the rendering information in the G-buffer feature tensors. For more details, we refer to our paper. Let us now look at how the perceptual discriminator works. The discriminator contains a robust semantic segmentation network and a network for extract.
Yo, imagine being that guy. Hey, guys, guess what? I've been working on the perceptional discriminator for over 2 years, man. It's going to be revolutionary. And people are like, man, shut your dumb ass. And then you come out with this. Oh, my God, that dude's... I don't understand why developers don't get laid more, man. Why are developers not treated like actors or athletes? It doesn't matter. They don't, look the best, or they're not chiseled like God. Okay? Gosh, they're devs. Give them a chance.
Perceptual features. In this case, a VGG-16. We extract features from the VGG at multiple levels and pass them through a convolutional network. This differs from prior work that trains discriminators directly on images. Training on VGG features allows our network to quickly learn a model of realism at multiple perceptual levels. We further pass the unmodified rendered image, as well as real images, through the segmentation network to obtain a label map for each. The label map is used to specialize the discriminator on individual object classes. Since we use a pre-trained, robust segmentation network...
Yo, they are not just... I just want people to know if y'all listening correct. Like, first of all, I seen Alchemy Gaming. My bad. He right. I assume there's no sexy devs. He right. You know what I'm saying? Because there is sexy devs out there. And I don't want to, make devs feel like, a body shame devs. Or, make them feel, what? Devs are sexy. You know what? Devs are the new sexy. How about that? The old sexy ain't even sexy. Devs the new sexy.
The object classes are consistent for rendered and real images. For more details, we refer to our paper. There is one more thing. For training discriminator networks, the common choice is to take in as much of an image as possible. The reasoning is that the more context of a scene the network sees, the better. We started with this strategy as well and found it to be suboptimal because scene layouts between real and rendered images can be quite different. Here we see the probabilities for each pixel to contain a certain type of object. The top row shows cityscapes, the bottom GTA 5. Images from GTA contain much more sky at the top, where cityscapes images contain vegetation. Images from cityscapes have a Mercedes star at the bottom. If we train our network with full images from both datasets, it will start adding Mercedes stars and place trees in the sky. We observe this effect in many other approaches. One part of our solution is to
Damn, yo, they not only just... I'm gonna let it play, man. I ain't gonna do it.
Decrease the field of view for the network and show it corresponding scenes from both datasets. When training our network, we sample rendered and real image patches that roughly contain the same things. This is done automatically and requires no access to semantic label maps. More details can be found in our paper. Let us now look at more results and comparisons. Here we see GTA again. And on the right, the results produced by our method.
Yo, that is freaky as hell. That is freaky as hell. Yo, imagine you taking any game that looks like this and putting it through. You can have brand new games just by putting it through a damn rendering system. Brand new games. So you can have one game and you can have somebody say, you know what? I'm going to put the entire game through my rendering system and I'm going to recompile it. And there you go. This is now an enhanced version. Yo, that is not. You know what? Do I got any sounds? I don't even know. There you go, man. Whatever that is, do that, man.
Here we see the results from classic color transfer. Color transfer matches the color distribution of GTA to cityscapes, but it does not modify images beyond the colors. Roads and trees keep their synthetic appearance. Unlike many other approaches, color transfer is temporally stable. Here is WCT2, a state-of-the-art photo style transfer approach. WCT2 requires a reference photo. It can become temporally unstable if rendered images and the reference diverge. Here we see again results from Cut. Cut commonly hallucinates objects like trees in the sky and the star on the hood. The sampling strategy of our approach alleviates such artifacts.
Yo, the amount of rendering that has to be done. What the hell are they using?
Here we see TSIT, an image-to-image translation approach. TSIT also requires a favorable reference photo, which may cause artifacts and temporal instability if rendered images and the reference diverge.
Damn.
Finally, let us look at GTA again.
Yeah, let's look at GTA, man.
And here's our method trained on the Mapillary Vistas dataset. Vistas features diverse images from around the world, recorded with different types of cameras. Our method captures the style of this data.
Hold up, I'm going back. Look at the T-shirt place on the right. If that don't look real, I don't know what to, man.
Finally, let us look at GTA again.
When they look at the stores on the right.
And here's our method trained on the Mapillary Vistas dataset. Vistas features diverse images from around the world.
Yo, it looked like a regular store, man. This is wild. Yo,
world recorded with different types of cameras. Our method captures the style of this dataset with its vibrant colors, while keeping the semantic and geometric content of the underlying game.
10 seconds, 10 seconds. Damn, that looked beautiful. We done, man. That's it. That's it. That's it. No more. No more. That's it. We done. You know what I mean? Hold up. Hold up, man. I see him calling in, man. I wasn't even going to take this call, man. He calling in. You know how I be. I sometimes just take calls, man. I get crazy in here. Kyle, what is going on, my man?
What's up, Nick?
Not much, man. What's up, man?
I want to fix up some misinformation here. You can't just remake games with this. This is taking hours to render that few-minute file, right? Like, that would take hours to render that. You can't just, and you can't, like, pre-render everything like that. That just doesn't work.
Okay, so Kyle, talk to me on that, okay? I want you to break it down. Now, for those who don't know, Kyle is my young OG, okay? Kyle has helped me with my webpage. Kyle has taught me as an old-ass man. Kyle has taught me, okay? So I got to give you your props first. But Kyle, so tell me, this rendering that's being done, you said how long it takes to render. So let me ask.
I know for sure, right? Like, it differentiates between different computers and stuff, but it will definitely take a long time. There's a machine learning algorithm, right? Like, you're taking source images and then you're putting it through that algorithm, which was trained with the city. I forget what they called them, images, right? And it's making those images look more like the image.
So let me ask, Kyle, do you think that any home user would have a system at home powerful enough to render even a scene in real time?
No way. Not real time.
Okay. All right. Now, from what I read in the article, I do believe they were using, I'm going to pull it up here, but I believe they were using 3090s. I put the link in my description too. But I believe they were using 3090s. And I don't, yes. Okay, so I'm going to just let people know how powerful it needs to be to render. So I am with you on that 120%. This is not something, you're going to be seeing within the next, couple years. It's not going to be even affordable for, anybody to even get graphics cards, multiple, that powerful. So I'm with you there, Kyle. So let me ask you this. As being the young guru you are, how far off in the future do you see us experiencing games where we can honestly run them through a rendering system in real time? How
Here's
far
the
away
thing,
are we
though,
from
right?
that? Okay.
Like, the computers get more powerful, the rendering system gets more demanding.
It does.
Right. So, if you're going to use the current time rendering system, it will never, like the highest end current time rendering stuff, it will never be able to real time, like with whatever that you have just laying around, right? Like, that's just how it is. And I can't say how long it's going to be because everything changes, like,
No.
everything.
No, and I'm with you on that, Kyle, but one thing I got to say, Kyle, to throw a wrench in everything you're talking about, if you go back, let's just say 20 years from me, okay, I'm 38, 20 years from me is 18, and I could even go back 30 years. We didn't have memory cards. We didn't have cloud storage. We didn't have a quick resume. These features would not even be thought of back then. So is it possible that we can see real-time rendering like this within the next, say, 20 years?